Hi, in this video, we are going to continue our series on JEE advanced problems. Uh, the problem that we are looking at is a multi-correct option objective. And we have this question. For any positive integer n, let S of n be a function defined from the domain 0 to infinity to R. And it is defined as this. Sn of x is the summation where k goes from 1 to n. Cot inverse this expression 1 plus k into k plus 1 x square whole divided by x, where for any x belongs to R, here x can be a real number, cot inverse x belongs to 0 to pi and tan inverse x belongs to minus pi by 2 to pi by 2, right? Now we have to select these options. Option A here, S10 of x and is equal to this. Option B is limit n tends to infinity cot of Sn x equals to x. And option C talks about S3 of x equals to pi by 4, whether this equation has a root in 0 to infinity, and tan Sn of x is less than equal to half for all n greater than 1 and x positive. So before we can start looking at the options in this problem, all you have to do is simplify this expression a little bit, right? So you might have seen how to handle these inverse trigonometric functions. This is a cot inverse. It will be better if we convert it to a tan inverse because we know identities for tan inverse. So what I will do is first try to simplify Sn of x, and after that we'll look at the options. Let's do it on the next screen. So Sn of x is written as cot inverse summation k goes from 1 to n, and it was cot inverse of 1 plus k times k plus 1 x square by x. Now what I will do is first I will convert this to a tan inverse. So cot inverse can be written as tan inverse 1 over x. So tan inverse it becomes x by 1 plus k times k plus 1 x square. And now think about it. This is a product of two terms, kx and k plus 1 times x, right? And we can see that x is basically the difference of k plus 1x minus kx. That will be equal to x, right? So we can split this tan inverse like this. K is equal to 1 to n tan inverse k plus 1x minus kx by 1 plus k plus 1 into k x square, right? And this fits in the formula of tan inverse x minus y by 1 plus xy, which is equal to tan inverse x minus tan inverse y. So I can write this as tan inverse k plus 1x minus tan inverse kx. This is a direct formula. You have to use that. And now you notice that the summation is over 1 to n. So this becomes a telescoping series situation where if you put k is equal to 1, you get tan inverse, you get terms like this, tan inverse 2x minus tan inverse x, that is the first term. Then you get tan inverse 3x minus tan inverse 2x when you put k is equal to 2, and so on. So you can notice that tan inverse 2x gets cancelled here. Tan inverse 3x will get cancelled with the next term. And finally, what you will end up getting is the first part of the last term. So tan inverse n plus 1x minus tan inverse nx. This tan inverse nx gets cancelled. This remains. And the first term, this part remains, right? So what you will end up getting here, after you do the telescoping series calculation, you will get tan inverse n plus 1x minus tan inverse x. So now we'll use this formula again. We'll say that this is equal to tan inverse n plus 1x minus x by 1 plus n plus 1x times x, right? So finally, we are getting nx on top, and I'll write it here. We are simplifying this whole expression Sn of x like this. We are getting it equal to tan inverse. On top we have nx divided by 1 plus n plus 1 x squared, right? This is my Sn of x, right? So now that we have this expression, now we can think of each of the options. So for option A, we have to figure out what is S10 of x. So that will be tan inverse nx by, so 10x by 1 plus 10 plus 1, so 11x squared. So that is my S10 of x. Now that is equal to pi by 2 minus cot inverse. Pi by 2 minus cot inverse 10x by 1 plus 11x squared. This is an identity. Tan inverse x plus cot inverse x is always pi by 2. So we can write it as pi by 2 minus tan inverse 1 plus 11x squared by 10x. Right? We have taken cot inverse and taken the reciprocal of that, right? Now, if you see, that is your option 1. That option 1 was actually asking whether S10 of x is equal to this or not. So that is obviously true, right? So option A is correct. Let's look at option B. Option B was asking us to find out the limit n tends to infinity of cot of S n of x and whether that is equal to x for all x greater than 0 or not, right? Okay, so we know the expression for Sn of x. Our Sn of x expression had come out to be this tan inverse nx by 1 plus n plus 1 x square, right? Okay, so this tan inverse we know can be written as pi by 2 minus cot inverse 10x by 1 plus 11x square. We can see that from here, right? So if I take a cot of this, so cot of S1 of x would be cot of pi by 2 minus this. So that is tan of cot inverse of 10x by 1 plus 11x squared. What am I using here? I'm saying tan of pi by 2 minus theta is equal to cot theta. And here the theta is what? Theta is this expression, right? So it is tan of cot inverse this. So that is basically tan of tan inverse of 1 plus 11x squared by 10x. And now that becomes basically 1 plus 11x squared by 10x, right? Okay. So now, actually, I should not have been using 10 here because 10 was for S10 of x. So I should be using n and n plus 1 here everywhere. So this is n and this is n plus 1 x squared, right? So this expression is actually 1 plus n plus 1 x squared by nx, right? Correct. So now if you divide by n up and down, we have this, I'll just write it here. Cot Sn of x is equal to 1 plus n plus 1 x squared by nx. And we have to do limit of n tends to infinity here, right? So if I try to do limit of n tends to infinity, the best way to do it is divide by n throughout. So you'll get 1 by n plus 1 by n plus 1 x squared by x, right? And we have to take limit n tends to infinity here. So this becomes clearly, this tends to 0, this tends to 1. So you get x squared by x, which is x. So we are able to show that limit n tends to infinity cot of Sn of x is clearly equal to x for all positive x's. So this B option is also coming out to be correct for us. Now the C option is basically asking us to check whether the equation S3 of x is equal to pi by 4. S3 of x is equal to pi by 4 has a root in 0 to infinity, right? So first of all, obviously we should find out what S3 of x is. So we'll just use the same expression that we have derived already and we'll try to see what is coming from there, right? Okay. So the idea is Sn of x was what? Sn of x was tan inverse nx by 1 plus n plus 1 x squared. So therefore, we can say tan of Sn of x is equal to nx by 1 plus n plus 1 x squared, right? Now, if you do S3 of x, n is equal to 3 if you put, right? You get tan of S3 of x is equal to, we are getting 3x by 1 plus 4x square. And if this equation is true, this equation is equivalent to tan S3 of x is equal to tan pi by 4, so 1, right? So this equation is equivalent to this is equal to 1, correct? So what we can see here is the equation becomes 3x is equal to 1 plus 4x square. So you have 4x square minus 3x plus 1 equals 0. So you can see that the discriminant is less than 0 for this quadratic, right? B square is 9 minus 16. So discriminant is negative, so it has no roots. So this quadratic has no roots, so option C is wrong. This doesn't have a root, right? Now, finally, we want to look at option D, where we have to check whether tan of Sn of x is less than equal to half or not, right? So option D, I will just state the option here. For option D, we have to verify whether tan of Sn of x is less than equal to half for n greater than equal to 1 and x greater than 0, right? So that is my option D. We have to check that. So we already know the expression for tan of Sn of x, that is this expression. So you have to check whether this inequality is less than equal to half for all n greater than 1 and x positive, right? So let's simplify this inequality. We know that n is positive, so this is positive, so we'll just cross multiply. 2nx is less than 1 plus n plus 1 x squared. So we have n plus 1 x squared minus 2nx plus 1 is greater than 0. We have to see whether this inequality is true or not. So first thing, this is a quadratic, so we should try and get the determinant of this quadratic. So the determinant of this quadratic, if you calculate, will be 4n square minus 4 times n plus 1, right? This is my determinant. Now this determinant for n is equal to 1, this determinant is less than 0, right? N is equal to 1, it is less than 0, right? So clearly if the determinant is less than 0, the quadratic will be positive, right? The quadratic will be above the x-axis if determinant is less than 0. So for n is equal to 1, this condition is true, right? However, for n greater than 1, right? So you can say that when n is greater than equal to 2, we can easily see that this discriminant is not negative. Because if you put 2, what happens? You get 16 minus 2 plus 1, 3, 12. So discriminant is positive. So if the discriminant is positive, the quadratic's graph will have two roots like this, right? So for n greater than equal to 2, the quadratic looks like this. So it is obvious now that it will not always be positive, right? The value of the quadratic will be negative between the two roots alpha and beta, right? So this inequality cannot always be true for all x, because when n greater than 2, the quadratic is like this, and when x lies between the roots, the quadratic is going to be negative. So our option D is also incorrect, right? So basically, this is how we have solved the problem. It was not very difficult. The main part is simplifying the Sn of x. Once you have done that, the rest of it follows in a pretty straightforward manner. You have to take limits. You have to check each option carefully, right? So that is what I wanted to show you in this question. We'll be bringing more problems for JEE Advanced. I'll try and publish at least 2-3 videos every day. So we'll look at all types of problems to prepare you for the upcoming exams. So I'll see you next time.